let's see, we already know how to actually take derivative of any function that comes your way, okay? If I give you any function, as long as I give you a formula, you should be able to find the derivative of it with all the techniques that we have discussed. Now, let us use this knowledge to try to solve problems. That's the whole point, okay? You don't do anything having this knowledge if you cannot use it to actually solve some problems, situations. All right, so the first application that we're going to discuss, and basically we're going to do this today, is about related rates. And these are going to be word problems, okay? So in the last homework that you had, you kind of, or the previous homework, I think it was homework 12, you had a hint of what this was, okay? When you had these triangles, and then there was this angle theta, and one of the sides was x, and you need to relate theta and x, and then find the rate of change of one with respect to the other, okay? So this is the kind of things that we're going to discuss now. And basically, like, let's just read this problem. So the variables x and y are both differential functions of t and are related by the equation, and then I'm already giving you the equation, how these two variables are related. And then the question is to find dy dt when x is equal to 1, given that dx dt is equal to 2 when x equals 1. So let me explain what's going on here. So first of all, what you can see here is that we have two quantities, namely x and y, okay? These are two quantities. This problem has no actual meaning behind the scenes, but the ones that we're going to do after, they will come from physical situations, okay? But right now, this is to get the idea how to solve this kind of thing. So you have two quantities, and it turns out that these quantities, they seem to be independent, but they actually depend on a common third quantity, which is t. I'm calling it t because typically in application, this is time. Like, there are many things going on, and everything depends on time, okay? Position, speed, and all this kind of stuff usually depends on time. So we have two quantities, and they both depend on a common variable, namely t. So let me just say here we have x, here we have y, but then they both depend on this common variable t, okay? So that's the setup so far. And in other words, x is a function of t, okay? Which we don't know the formula, but it's a function of t, and y is also a function of t. We're being told that. And moreover, we're being told that they're differential. In other words, you can take the derivative of these functions with respect to t. That's what that means. Next, the next piece of information is that we have a way to relate these two quantities, okay? So x and y are related via that equation over there, okay? This equation is not telling you anything about t. There is no t in there, but it's telling you how x and y are related. And with that information, our job is to figure out what's dy dt when x is equal to 1, okay? So, of course, to answer a question like this, it's actually pretty straightforward. What you have to do is take derivative and use implicit differentiation, okay? Because remember, y and x, they are both functions of t. So, let me write here solution. I'm going to emphasize and write as y of t, so you understand what's going on better. So this is what we have, right? And then our job is to figure out what's dy dt. So let's take derivative with respect of t, okay? So we apply dy dt. So apply derivative with respect of t to both sides. Let's see, who can tell me? What do we get on the left? If I take derivative with respect of t, what do we get? Y prime, or dy dt. In these things, in this type of problems, since there are too many variables going around, I strongly encourage you to use Leibniz notation. Because if you write y prime, what do you mean? Do you mean dy dt or do you mean dy dx? Because I could ask you for dy dx in there. Because y is a function of x as well, as you can see. Yes? So here, this comes in very handy. So it's very important that you tell me with respect to what variable you are taking the derivative. So dy dt is going to be equal to, now what's the derivative on the right hand side? What do you think we need to do? Yes?
It would be 2x plus 1. No, 2xt. All right, that's not right.
But, listen, so you are more or less on the right track, but you're missing something. Yes.
Will it be 2x times x prime?
Dx dt. Remember, don't tell me x prime. You tell me x prime, it's not clear what variable it is. So remember, we're taking derivative with respect of t. So what is this? It's the composition, right? So this is the, if you want, the t square function composed with the x function, right? So it's the composition, so you need to use chain rule. So that would be 2x times dx dt. Do you understand this? It's chain rule. Okay, and then of course plus 0, so the 0 doesn't count. So now, notice that what we had before was an equation relating the quantities, relating the variables in question, and now after taking derivative, what we have here is another equation that relates their derivatives, okay, or their rate of change. So that's why this unit is called related rates, okay, because here we have a relationship. From the relationship between x and y, we obtain a relationship between their rates with respect to t. Okay? So dy dt is related with dx dt like so. So now the question is pretty straightforward. So find dy dt when x is equal to 1, given that dx dt is equal to 2 when x is 1. So let me kind of tell you why this is being told like this. So what is x equal to 1 in this context? So remember, x is the same thing as x of t. So when I say that this is equal to 1, in a sense, because here I'm not talking about t at all, I'm not giving you any information about t, but this is a way for me to fix a value for t. This is a way to fix a moment in time. So at this moment, when x is equal to 1, it's like saying, for whatever t, x equals 1, at that moment, I want to know how fast y is changing with respect to time. That's the question. Okay? So this is a way of fixing this moment in time. And notice that that's all we need. So to find dy dt at that moment, all you need to know is what is x and what's dx dt at that moment. Do you understand this? Let's look at the equation. To find this value, you just need to know this value for x and this value for dx dt, and all of that is given to you. Okay? So, but there is a meaning to this. Basically, I'm actually fixing a moment in time here. Okay? So, if you want to know dy dt when x equals 1, but understand that this means at this point in time, this is just 2 times 1, because that's what x is equal to 2. That's what x equals to times, and what's the x dt at this point in time? Is equal to 2. So what's the answer? 4. Again, if you ignore everything I've said and you just look at what I wrote, this is pretty straightforward, okay? You have your equation, take derivative, make sure that you use chain rule because the derivative is with respect to this common variable t, not with respect of x or with respect of y, okay? With respect of t, so you have to use chain rule all the time and then plug in your data, okay? That's the general situation here. Now, of course, what's going to happen is that you're going to be given a word problem and this is not going to be given to you. Actually, none of this is going to be given to you explicitly. It's your job to identify the quantities, identify the equation that relates the quantity, and then you activate this procedure. Okay? So this is the kind of things that we're going to practice now. Okay. Questions on what I just did here. Now we're going to do several examples to hopefully get you up to speed with this idea. But do you have any questions on this?
Is this on our test?
What do you think?
I just came, sorry.
No, this is new material, right? Well, I should say yes. It's just that it's not on this test, it's in the next one. Right? So it will be on a test. Okay. Any questions on what I just did here? No? Okay, so then let me summarize what I told you and then let's jump into examples. So, by the way, this is what we generally call related rates. I already told you why we call it like that, because you have a relationship between the variables. They depend on a common variable, those two guys, and then by taking derivative with respect to a common variable, we get a relationship among their rates. Okay, that's why it's called it. All right, so let me write here general strategy. And then let's try to apply this strategy to the problems that we are given. General strategy for related rate problems. Okay, so the first thing that you need to do, well, actually, I should say here, the zeroth thing that you should do. Like I said, the problems are gonna be word problems. So what do you think is read? How many times?
Twice.
As many times as you need until you understand what that paragraph is telling you. You don't need to know how to solve it. I mean, that's what you're gonna try to do then, solve it. But you have to make sure whenever you have a word problem, you have to read it, and read it until you understand what it's telling you. Okay? So read the problem. Okay? Read the problem. And if possible, let's see, if you have some experience in solving word problem, if possible, what else you should do?
Highlight the most important part of the word problems.
Okay. But what else is, in mathematics usually, what else is helpful when you encounter a word problem?
Identify the given information and the numbers.
That will be some of the things that you do later. But once you read, what you should do as you read?
Identify what it's asking.
Yeah, well, that's actually similar to what your classmate said. Okay, so maybe you're not used to this, but usually a picture helps. So every time that you have a word problem, you read it, and if you really understood what you read, draw a picture of what you read. A little diagram, whatever it is, you don't have to be casual. Just do something that you can visually relate to with what you just read. Do you understand what I'm saying? This is gonna help you identify the things that you need. Okay? Otherwise, you'll just be looking at a bunch of text and then you can get lost pretty quickly. However, if you summarize the information in a picture, it's easier to go from there to hopefully find a solution. Okay? So, if possible, draw a picture. If possible, sketch a picture. Okay? Just, to help you out. So you're gonna see me sketching pictures of the problems that we did, just because I think it's easier to understand what's going on if you're looking at something. Okay, so you already read the problem. You have an idea of hopefully what the problem is telling you. So what's the first step? Well, the first step is to actually identify the quantities that are being discussed, right? The quantities that we are interested in. So identify the quantities involved. For example, in this problem above, which again is not, it has no particular meaning because I didn't tell you where these quantities are coming from or whatever. But how many quantities do you see in this problem?
2.
How many do you see?
5. 2x, y.
5. Okay, where are the four?
I think x, y, the equation, and then dx, dy, dt.
Oh, equation something. Quantities.
Okay.
Quantities. So there are 3 quantities. What are they?
X equals 1.
No, quantities.
X, y, and t.
X, Y, and T. Okay? So here we have X and Y, and then of course there is this secret quantity T that, everybody depends on that one, even though there is nothing going on with T in this equation, but we know everybody depends on T. Okay? So there are 3 quantities here. So the first thing is that you need to be able to identify the quantities involved. So what's the second step that you should do? Once you identify the quantities, then go ahead and identify all the data, all the information that you have provided about these quantities in the problem. Okay? So identify the given information. So you identify the given information and also identify what is it that you need to find. Okay? Identify the given information and what you need to find. Okay? Identify the given information and what you need to find. Okay, so once we have done this, so you know your quantities, you know all the information that's given to you, and what you need to find. The next step is, okay, now it's time to go back, look at your quantities, and relate it. Try to see if you can find a relationship among your quantities. Like for example, somehow try to see how you could come up with this equation. Okay, of course the problem will tell you how to do this. Okay, well, it's not going to tell you explicitly, but you have to read between the lines and understand the situation, and then be able to figure out a relationship among the quantities. All right, so relate the quantities. Relate the quantities, and you know, typically this is via an equation or formula. Okay, maybe one of the quantities is volume, something, and then you know, use the formula for the volume of whatever shape you're provided, and so on. So identify the quantities, identify the given information, relate the quantities, and once you have your relationship among the quantities, then take derivative, and so on. Okay, so take derivative and with respect to the common variable, and solve. Take derivative. With respect to the common variable, you know, typically this common variable is time, is t, and solve. Okay, and solve for the desired information. Again, this is just a general guideline of how to approach the problem. Okay, every problem is going to have its particular, you know. For example, I will say maybe the most challenging step is number 3. Okay, to actually figure out how you relate those quantities, and this is on a case-by-case basis, depending on the problem, is what you do. But hopefully, we're going to do enough problems that will give you a feeling on how to do these things. So we are about to use this strategy now for several problems. Are there any questions on what's written on the board? Okay, so let's take this into practice. So the plan is to do 4 main examples, okay? So just to give you an idea, the first example is going to be ripples in a pond. So we're going to throw a stone in still water. And what happens when you throw a stone in still water?
It sinks.
Okay, yes, but like the name suggests, ripples in a pond. So the stone sinks, but then what else happens? Then, you know, a wave created, right? Ripples. We're going to assume that they're concentric circles, right? We start getting a bunch of circles. We want to figure out how fast these circles are moving at a certain point in time, okay? That's what we're going to do here. The second one, we're going to be inflating a balloon. When you inflate a balloon, what's going to happen? It gets bigger and bigger. So in particular, the radius is increasing at a certain rate. We want to figure that out, okay? How fast is the radius of this balloon increasing at a certain point? This one, we're gonna have a little camera following an airplane or a rocket that's shooting up, and this camera is gonna be moving and following the rocket as it goes up. We want to figure out how fast it's rotating at a certain point in time, the camera. Okay. And for the last one, we're gonna have a tank, a conical tank that is getting water, and we want to figure out how fast the water level is rising inside the tank. Okay. Those are the kind of applications that we're gonna see in here today, and in the homework you're going to get others. But again, this is the general strategy to deal with those problems. Okay? All right, so let's go. So the first one, ripples in a pond. So again, the first thing that we should do is let's just read. Make sure that we understand what's going on. So a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Okay, so again, read it again on your own to make sure that you understand what this paragraph is saying. I'm going to draw a little picture just to have a visual representation of what's going on. Okay, so we throw the stone somewhere. So let me put it here. This is my little stone, and then when we throw the stone, what's going to happen? ripples start to be created, and we're being told that these are concentric circles. So I'm just gonna draw circles around, right? As time passes, more and more circles are created, and by reading the problem, we should focus our attention on this guy, the outermost one, right? Because this is the first one that was formed when we throw the stone, and then it's expanding as time goes by. Do you understand this? Okay, so do you understand the situation? What's happening? Pretty simple. Throw a stone, ripples start forming, right? So let's try to identify what are the quantities that we are interested in. So let's read the problem again. So pebble is dropped into a compound, causing ripples in the form of concentric circles. Okay, so what we have here are circles, right? And then they're talking about the radius of the outer ripple. So we want to focus our attention on the outermost ripple. In particular, we're interested in the radius, right? Remember, the radius is like the defining property of a circle. Together with the center, which, okay, you throw the stone somewhere, that's the center, the radius tells you everything about the circle after that. So, here we have blue. Okay, so I'm gonna be following this R, okay? So as one quantity, does everybody agree? That's one quantity that we have. So step number one is let's identify the quantities. So we have R, okay? And we say that this R, I'm gonna leave a space, and this represents the radius of the outer ripples. Do you understand this? That's the first quantity. Okay, let's keep reading and let's see what else are we interested in. Okay, so when the radius is 4 feet, it's still talking about the radius. At what rate is the total area of the disturbed water changing? Now, they're talking about area. The area of what? The area of the outside of the outer circle. So you understand this? Because inside this outer circle, that's the region of the disturbed water. Outside of the circle, the water is still. And what's going on is that this circle is expanding, and then, it's disturbing the water around. But basically, our focus always is this outer ripple. Do you understand this? So, as another quantity that we have, that's A, which is the area of the outer ripple. Because, the disturbed water is everything that's inside the outer ripple. So the boundary of the disturbed water is the outer ripple. Yes? Okay, so we have those two. Is there anything else? So remember, we need to always look for a common variable. Okay? Just think about the very simple example that we did first. So what do you think is the common variable here? The common quantity among these two. We have the radius, we have the area. Do they have anything in common? Where is it? Okay, so that's units. Those are units. I'm talking about still quantities. So R is a radius, that's one quantity, and we have the area. What do they have in common? Diameter and radius is essentially the same idea.
Increasing.
Okay, they are increasing, but how do they increase? When time passes. Time, I told you at the beginning, time is usually your common variable. All of this is happening, even though the problem is not telling you, this is happening as a function of time, right? It began when you throw the stone, and then as time passes, the whole process starts to activate. Yes? So even though they're not telling you, both of these guys, they are functions of time. So R is a function of time, and the area is a function of time. Do you understand this? As time goes by, both of these quantities, in this case, they are increasing, both of them. So here we have our third quantity, T, and T represents time. And it's very important to have the units clear, the units that we're using. Okay, when you solve application, the units are important. Typically, we write the units in square brackets. So let's see. The radius, what units are we using for the radius? So we're using feet for the radius, right? So we're using feet here. What units are we using then for the area?
Feet squared.
Feet squared. And what units are we using for time?
Seconds.
Very good. And that's kind of implicit right here. Yes? When they say that the rate at which the radius is increasing is 1 foot per second, right? So time is being measured here in seconds. So I think these are all the quantities that we need for this problem. If, it could be that you don't see a quantity and then as you start working on the other steps, you realize that you need something else and then maybe you go back and revisit and then see if you can figure out the other quantity. But this seems to be everything that's going on here. We have, focus is on this outer circle and then what do we care about it? The radius, the area, and then we need to find something common to all of those, and that's time. So every time that you find a quantity, make sure that you understand that they have to depend on a common variable. Okay? And like I said, typically it's time, but make sure that time makes sense in the problem. Okay? In this case, everything is happening as a function of time. All right, so we have our quantities laid down. Any questions? Okay, now we need to, step number 2, what do? Identify the given information, right? So now we have in terms of the quantities, of course. So now given data or given information, however you want to call it. Okay, we read again, but now having in mind these quantities, okay? So if ever is drop, okay, nothing going on there. Causing ripples in the form of concentric circles, okay, we already used that information, like for our pictures and so on. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. Okay, so that sentence is giving you a data. What is it? Very good. Remember, this word rate is a key word for what? For derivative. So you understand this. Remember, derivative is rate of change, right? So rate is a key word for derivative. So here, in this information, they are giving us dr dt. Here is very important, don't write r prime, write dr dt, because we need to know with respect to what variable this is changing. So we are given that dr dt, what is this equal to? What is this? 1. This is 1 foot per second. And remember, they are telling us that this is constant, so dr dt is always 1. Okay? It's given to us, no matter what time we're talking about, this is expanding at a constant rate. Are we okay with this? Okay, so you can think of this as the speed, because remember that because r is in foot, so this is a unit of distance, of measurement. So the rate of change is the speed of what that quantity is changing. Okay, so this is changing at a constant speed, 1 foot per second. All right, so let's keep reading, see what else we're given. So when the radius is 4 feet, okay, that's it, we're not given anything else, and then we're being told when the radius is 4 feet, notice that they never talk about time, but by saying that r is equal to 4, we are fixing a moment in time, right? That moment in which the outer circle has a radius of 4 feet, at that moment, I want you to tell me how fast the area is changing of the stopwatch, right? That's really the question. So, what is it that we need to find? Are you sure? Read. What rate is the total area changing? So what does the word rate means? So we need to find dA dt, right? So our job is to find dA dt when? When r equals 4. Do you understand this? So we're not giving more information. So we're being told that dr dt is 1 feet per second, so it's constant. And then with that information, we should be able to figure out how fast the area is changing when r is equal to 4. Again, this is a way of telling you, of fixing a moment in time, indirectly. Is everybody okay with this? Okay. Questions? No? All right. So, okay, so we have our quantity, we have our data. Now, what's step 3? time to relate the quantities, right? So relate quantities. So what are the quantities in question here? What are the main quantities in question here? So R and T, but the main ones are R and A. Remember, T is this secret quantity that's working behind the scene, right? We're not being told anything about time, really. So it's just this quantity that we know both of these variables depend on. So it's A and T. Those are the main quantities. Remember, that's what this is about, right? So we need to relate them. How can you relate these two quantities? Very good. I mean, what's A? A is the area of a circle. What's R? R is the radius of that circle. So how do we relate the quantities? Use the formula of the area. What's the area of a circle? No.
E times r squared.
Yeah, pi r squared. Yes. So the area of a circle. So you need to know the area, the formulas for the basic shapes, like area of a circle, of a triangle, the volume formulas for a sphere, pyramid, all that kind of stuff. Yes. Make sure that you find them, you know, and little flashcards and learn them. Okay. All right. So relate the quantities. In this case, straightforward. A is pi r squared. Right? That's the formula for the area of a circle. Does everybody understand this? Okay. Now we have a relationship. What's the next step? Remember, you want to. This is what we want. We want dA dt. So if we want dA dt, what do we need to do? Take derivative, right? Now remember, these are functions of t. So when you take derivative, remember to use implicit differentiation here, or chain rule. It's the same thing, or you want to call it. Okay. So step number 4, find the rates. So dA dt, what is it? It's going to be equal to pi, that's a constant, times 2r times dr dt. Chain rule. By the way, this is super review for the exam because half of the exam is using chain rule, if not 80% of the exam. I mean, that's the most important rule that we have out there. Okay. Do you understand this? Now at this point, what do? Plug in our given data and solve what you do. Okay? So, in other words, so this is equal to 2 pi r times dr dt. And now we're going to plug in r equals 4. Okay? So r equals 4 is going to give us then a dA dt evaluated at r equals 4. So at this point in time, it's going to be equal to 2 pi times 4. And what's dr dt? Remember, that's equal to 1, regardless of what is r. We're being told that the radius is increasing at a constant rate. So what's the answer? A pi. And what are the units?
Per second.
Square feet per second. Remember, this is area. So a pi square feet per second. That's how fast the area of the stored water is changing at that point in time. The fact that this is a positive number means it's increasing. Okay? All right. Questions? I mean, typically this goes way faster once you get a hang of it. It's just that I'm talking a lot because if this is the first time that you see word problems like this, you need to have a certain mindset for this. Okay? Notice that none of these formulas that were given to you in the problem, right? The problem tells you the situation, and then from the situation, you get the formula. And once again, the picture is not especially helpful in how you do this, but it's helpful to fix an idea in your mind and to hopefully see what's happening. Okay? All right. Questions? No questions? Okay, so let's go to the next one. The Let's inflate a balloon. All right. So something else also is that you have to understand what type of units. So let's see, how do I say this? Given a quantity, what type of units correspond to it. For example, when we talk about a quantity, a linear quantity, something that is about measuring something, what type of unit are you looking at? So, you know, units of length, right? They have to be linear units, right? If we're talking about area, what type of units are you looking at? Square units. If we're talking about volumes, what type of units are we looking at? Cubic units. So sometimes they may not use the word area, they may not use the word volume, but when they put the units is gonna give up, is gonna give away what are they talking about. Okay, so it's important to understand this. For example, here, you know, if you know the parentheses, because I put the parentheses there to help you out with the formula, but if you know the parentheses, the problem is ended where it says 2 feet. The word volume is never written anywhere. But the first number that shows up kinds of give it away when you look at the units. Okay, by telling you cubic feet. You should already, the word volume should be in your mind. You see that. Okay? All right, so let's read. So air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Okay? Find the rate of change of the radius when the radius is 2 feet. In other words, how fast is the radius growing at that point? Okay? When it's 2 feet long, how fast is it growing? Okay? And then I'm reminding you the formula for the volume of the sphere, if you don't remember, which is 4/3 pi r cubed. Okay? That's the formula for the volume of the sphere. Why a sphere? Because we're dealing with a spherical balloon. Okay. All right. So I mean, here maybe the picture is not especially helpful, but I'm gonna do it anyways. So we have a little balloon. You know, it's a sphere, and then it's a little opening here, and then air is coming in to fill in this balloon. Okay, just putting air into the balloon. Now, actually, I'm gonna take advantage of the picture, and on the picture, I'm gonna put the data that we have. So this is a spherical balloon, so it has a radius, sphere, so there is a radius. And also, we're being told that the rate is being pumped at a constant rate. Notice they don't use the word constant, but it's implied because they say 4.5 cubic feet per minute. So that means it's constant, right? So let me write it here. So the rate at which this is happening is 4.5 cubic feet per minute. Okay. All right. So that's a picture showing up the situation. So let's activate the process. Step number 1.
Quantities.
So figure out the quantities. What are the quantities in this problem? So what's R? You always, every time that you are doing a word problem and you introduce a variable or a quantity into a problem, you need to tell me what it is. You need to tell me what you mean by R. So what do you mean by R? Of the radius of the balloon. Okay. Remember, you may have a problem in which there are several things going on. So you need to be very specific when you identify something. So R stands for radius of the balloon. Okay. And what are the units?
Cubic
Feet. R is a unit of distance. It's a unit of length, right? It's a quantity that measures the distance of something. It's a radius, so it's distance. So the units here are feet, just feet. What else? What else matters here? What other quantity? Okay, but that's the rate of something. So we are in the quantity. So the rate of what? What's the quantity that we are given the rate of? Volume, right? So volume is another quantity. So the volume of the balloon. What are the units here? Cubic feet, right? And as usual, does everybody understand that both of these quantities depend on time? You're blowing the balloon, as time passes, then the balloon is growing, right? So there is a secret variable here, which is time. And the point is that both of these guys are functions of time. So it's good to stress it. So write this down. So you're stressing that, okay, my main quantities are radius and volume, but how are they actually interconnected? Well, they both depend on time, okay? And then that's gonna help us find the stuff that we need. And how are we measuring time in this problem? In minutes, right? It's giving the data, 4.5 cubic feet per minute. Everybody okay with this? All right, so we have our quantities. Next, what do we need? Data. All right, so let's see, what are we given? Now remember, the data we write in terms of our quantities, okay? So you go back and read, we find a number. What does that number represent in terms of quantities?
Derivative volume.
With respect to what? With respect of t, so that's dv dt. Does everybody understand this? So we're being told that dv dt equals 4.5, right? 4.5 cubic feet per minute. In other words, it's constant, right? So the rate at which the volume is changing is constant. Okay, and then what else? That's it. So now is the question: what is it that we need to find? So we need to find the rate of change of the radius. That's dr dt, right? When? When r equals 2. Remember, that's a way of fixing a time. Okay. So then we need to find dr dt when r equals 2. It is okay? Okay. So what's step number 3?
The equations. I mean the quantities.
The quantities. So let's do that. So relate quantities. And remember here, quantities is radius and volume of a balloon or of a sphere, right? The balloon is spherical. So how do we relate these guys? Via the formula, and I gave you the formula right here, right? So here you don't really need to work too much. So we can relate them via this formula. So V equals 4/3 pi r cubed. Okay, now what do we do? With respect to what? You have to be careful. You say take derivative, then you may think with respect of r, and then just bring the 3 down, subtract 1, and then right. So it's important here with respect of what variable? T, right? So take derivative with respect of t. Because why? Well, because that's what we want. We want dr dt. Everybody understand this? We want dr dt. Okay. So then step number 4. Find derivative. I guess just gonna say find derivative with respect to t. Okay, so we have dv dt. That's gonna be equal to 4 pi r squared. That's it. That's it. Or should I write something else? Times dr dt.
It's 4 pi over 3.
Yeah, but the 3 comes. Okay. When you take this derivative, the 3 comes down, get r squared, and the 3 cancels this 3. Yes? So, dv.
I'm confused because I thought they give you dv over dt.
Yes?
So how come in the other problem it was the other way around?
What do you mean the other way around?
Like when you did to find the rate.
Because they give you dr dt in the other problem, they didn't give you dA dt.
Oh, okay.
I mean, now we're going to put the data.
Yes.
Okay.
Now I understand.
Okay. So, because v equals 4/3 pi r cubed, that means that dv dt equals 4 pi r squared times dr dt. Do you understand this? Now, let's put in, And you need to understand what is it that we want. This time we want this guy, right? And we're given this one, so that's fine. So let's just plug in and then we solve. Or if you want, before you plug in, you can solve for the RDT and then you plug in whatever you like best. Okay? Let's see, I kind of like that way we have a formula. So this means that DRDT, why am I doing this? Because that's what I want. I want DRDT. DRDT is dVdt divided by 4 pi r squared. So this is a formula of the rate of change of the radius with respect to the rate of change of volume on the other one. Now let's plug in. So what do we plug in? R equals 2. So when R is equal to 2, we get dr dt. Now dVdt happens to be a constant all the time, regardless of what the radius is. So that's always 4.5. And then here we get 4 pi times 2 squared. Everybody okay with this? All right, so let's do this. So let's see, 4.5, I want to get the exact answer. So that's the same thing as 9 over 2. And then this is 4 times 4, 16. That's 16 pi. So it's going to be 9 over 32 pi. Okay, that's the exact answer. And what are the units? What are the units?
Feet per minute.
So this is dr dt, so the units are feet per minute. Okay. Now, if you want to get an idea of what this is, yeah, just 32 times pi, and then do 9 divided by that. So that's about 0.09, so it's 895, so feet per minute. Okay, but again, this is an approximation. This is the exact answer, right? Okay, any questions? What happened? Why do you look puzzled?
No, I don't know, I don't understand what you did. Like, if I was given that question, I wouldn't be able to do the last part.
What last part? Let's see. Explain yourself. What line? Are you okay up to here?
Yes, I understand that, but after
Okay.
that, like, I don't know, I got confused.
What's step number 4?
To find the rate?
To find the rate. Why? Because that's what you need, right? You need dRdt. This is what you want. So you need the derivative.
Yes.
Okay. Do you understand this line? Took derivative. The derivative of b with respect to t equals this. Because if b equals this, then dVdt equals this. Yes? Do you understand that? Yes or no?
Yes.
Okay. Now all I did was I solved for dRdt because I want dRdt. I just solved for it because I like to see a formula for it. Just divide by this. That's all I did. Now let's plug in what we're given. What are we given? We're given that dVdt is a constant actually, it's always the same thing. Right? So instead of dVdt, I put 4.5. That's what it equals to. And R is equal to 2 because we want to know what's dRdt when R is 2. You see, R equals 2. Let's put 2 here for R. Calculate. So what is it that you don't understand?
It's fine.
No, it's just
No, it's fine.
I want you to understand that this is not. I mean, if the hard part is to get here, after this is automatic. After this is like the first example that we did. Take derivative, plug in your stuff, and find the thing that you are looking for. The hard part is to get here. If you get here, then the rest will be easy. As long as you can take derivative, of course, and so on. But once you have this, you take derivative and plug in. Yes, if you don't like the solving part, then ignore this line right here, plug in your stuff. Here you put your 4.5, here you put your 2 squared, and then solve for the dRdt. You get the same thing. Right? So, yeah, the hard part is up to here. Okay. Questions? Yes.
On the test, would you want the exact answer or the approximation?
If I don't tell you anything, I want the exact answer. If I say round your answer to this many decimal places, then you round. You always want to know the exact answer, right? But if typically that's what I'm looking for. I want to see a exact answer. But it's good to write this just to have a feeling of what it is. Because if I tell you this, maybe you don't know. Okay, why is this? How fast is thing going? Well, it's about 0.09 feet per minute. Okay, so. Okay. Questions? I'm still confused. What is confusing from this? So help me because I don't know. I think it's pretty clear. Should I explain? I don't know how to explain this in a different way. I think this should be straightforward. Does everybody understand this? Okay. Remember, once you have your equation, you take your derivative. At that point, just plug in what you're given. Just plug in and solve what you need. Okay. You're given R. You're given dV/dt. Plug it in and solve for what you need. That's all. Okay. All right. Okay, so let's see. I'm gonna give you you take attendance, and as I do so, try to do this problem. See if you can do it on your own. Okay, so let me first at least give you the picture because and then once you have the picture, it should be easy. So a camera is mounted at a point 3,000 feet from the base of a rocket launching pad. If the rocket is rising vertically at 180 feet per second, when it is 4,000 feet above the launching pad, how fast must the camera elevation angle change at that instant to keep the camera aimed at the rocket? Let's see. Do you understand what this is saying? Do you understand the situation? Let's see, if you were going to draw a picture of this situation, how would the picture look like? Very good. Can everybody picture the triangle in your minds? Okay, good. That's good. So, I'm just gonna draw something here, all right? So, here we have the floor, right? That's the floor. Then, let's say that over here we have the launching pad. So here, this is the launching pad. Okay, and the rocket was launched, and then it's somewhere in here. Okay, I forgot how to draw a rocket, so I'm just gonna do something like this. Whatever, just assume that that's a rocket. Okay, so the rocket is launched. Okay, and then remember, it's telling you that 3,000 feet from the base, so the rocket is launched from here. Then somewhere 3,000 feet from the base, so somewhere in here, 3,000 feet away, we have a little camera. Now, you should understand, initially, we want the camera to always be looking at the rocket, right? At the beginning, the camera is like this, right? It's pointing where the rocket is. And when the rocket is launched, then as the rocket rises, the camera has to be changing and adjusting its angle, right? So it's pointing always at the rocket. Do you understand this? So if we take a snapshot of that moment in time, of this scenario, if we take a picture, we get a situation like this. So somewhere in here, we're gonna have our camera, whatever, let's say this is the camera. And then remember, the whole point is that we want the camera to always be looking at the rocket. Do you understand this? So that's something that's gonna be, and because the rocket is going up, hopefully, this camera is going to be changing its angle of elevation. In other words, there is an important data here, which is an angle, right? This is the angle of the camera, which is going to tell you the rate of change of this angle, tells you how fast this is rotating. Yes? It's really the question is how fast this angle is changing. And, the assumption here is that this is 90 degrees. Let's complete the data. How much is this distance? That's 3,000 feet. And I don't know, because we're doing this as a function, we're modeling the situation. We can call this something. What letter would you use for this? For this quantity over here? H, or the height of the rock, right? And call this H. And then it may not be needed, but let's see, is this needed? This is the difference between the rocket and the camera. For example, in the homework, you were doing a problem in which this quantity was important. It was the distance between what you had down here and something that was going on, okay? Now, in the problem, it doesn't seem to tell us much about it. But anyways, I'm just going to put it here just for simplicity, okay? So I'm going to call this D. And D represents, stands for the distance between the camera and the rock, okay? I don't think that's going to play an important role here because there is no mention of that distance in the problem, but, it's part of the picture. So when you have a right triangle with the situation model, is it clear what's going on? Now, try to see if you can solve the problem. We kind of already have the quantities in the picture, by the way, okay? As I said, I put D there for completeness, but you don't really need it, right? Because it doesn't seem that you need it. Yes?
Don't we have H, right? It says 4,000 feet above the water.
And that's for the data part. That's a moment in time. But here I'm showing you the picture, right? The general situation. The rocket is launched and you have your camera. If you take a picture at some moment, for example, at that point in time, when is it? When the height is 4,000 feet. So when this is 4,000, you take a picture, this is what you see. But when it's 5,000, you also see this. And when it's 3,000, you also see this, right? So this is the general situation. And then when you solve the problem, the last step is to actually plug in those numbers, right? But first, you want to model the situation. All right, so give it a try. I'm gonna this. Okay, H. What does H represent? Okay, so height of the rocket. So height of the rocket. Okay, rising vertically, let's say at time t, right? So a specific point in time. Okay, good. And what are the units for this? Feet. Okay. What's another quantity that we care about? Theta. So remember, velocity that comes from, if you want to talk about the velocity of the rocket, that's just the AGT, right? That's the rate of change of the height. So that's already kind of including that one. Okay, so theta, that's another quantity. Does everybody agree that theta also depends on time? And what does theta represent? The angle of elevation of the camera, right? And what are the units here? So you need to understand what units that you're going to use. So typically in these problems, you want to work with radians. Okay. Now, if you want to give the answer in degrees, once you get your answer, because you see, we are going to be mixing this theta with other things. So you should expect your values here to be in radians. If you want it in degrees, it's okay. Then just convert to degrees. Okay. So let's put radians here. Okay, so, and then we have time, right? So we have t, which represents time. And it's clear that all of this is depending on time. And what's the unit for time in this problem? So seconds. Good. Okay, so we have our quantities. What's the next thing that we need to figure out? Data. All right, so what's data? It's kind of summarized already in the picture, right? So what's the data? Data always about the quantities, okay? So what data are we providing?
Well, we have of the height with respect to the time, which is A.
So does everybody understand what this number represents? That's dH dt. Yes? But remember, speed or velocity. First of all, by looking at feet per second, you should understand that that's talking about speed. About speed, right? Or velocity. You want to call it velocity. And you also need to understand that velocity is obtained by taking the derivative of the position function. Here, our position function is the height function, right? That's the position of the rocket.
So 3,000 altitude would be the height?
No, 3,000 is this distance here that is going to come into play later, but it really doesn't tell you anything about these quantities. 3,000 is just telling you that this camera, the camera about this guy, is 3,000 feet away from the base of where the rocket is launched. We're going to use that later when we try to relate the quantities. Okay, the 3,000 will be important, but 3,000 really is not playing a role at this moment. Do you understand this? We want to figure out the data about the quantities. So we counted this number, and even though they don't say it, you should understand that that's dH dt, right? Now, is this constant? In other words, is dH dt equal to 880? Or is 880 at a given moment in time? At a given moment, you have to read carefully. Notice that it's not telling you that it's rising at this speed all the time. It says if the rocket is rising vertically at 180 when it is 4,000 feet, in other words, at that moment in time, that's speed. As you know, that's accelerating. Acceleration is speed changes. So as time changes, your speed is going to change. Do you understand what I'm saying? Okay? And it has to accelerate because it has gravity and all the stuff working against. Anyways, so this time the density is not a constant, but it's telling us that at this point in time, so when h is 4,000, when h is 4,000, the dht is 180. Is it clear? It's different from the previous situation. The previous problems, the rate of change of one of the quantities was constant, right? dvdt and drdt for the ripple sample. Here, the dht is not a constant, but that's okay. Anyways, we are interested at this moment in time. The problem is about this, right? When the height is 4,000. Okay, so the speed of the rocket at this moment in time is 180. Yes? Okay, and then the question comes. What's the question? What do we need to find? So how fast must the camera of elevation change? In other words, what's the rate of change of theta? In other words, what's the theta dt? Right? Speed of the camera. Like how fast is the camera moving to keep up with the rocket? Yes? So the theta dt. So we want to know what's the theta dt at this moment, right? When the height is 4,000. This is the question. Do you understand this? Okay. All right. Now let's go to step number 3. What's step number 3? So let's relate the quantities. I mean, you should understand. You don't have to write all the things that I'm writing, but this is a way to organize your ideas, to organize a problem, so that you can understand what you're doing and that somebody else can read and understand what you are doing. Okay? Remember, typically when you write stuff, you write for somebody else. So you have to make sure that you do it in such a way that whoever comes can read what you are trying to do. Okay, so let's relate quantities. So the quantities here are height, h, and theta. Now here, situation like this when the picture is super heavy. Okay? Go back to the picture. How can you relate h and theta?
Tangent.
Tangent. Does everybody understand that you should think about tangent here? Okay, good. For example, your classmate originally wrote inverse tangent. That's fine. But I would consider inverse tangent a little bit slightly more complicated than just using tangent. Okay? You use whatever you like. If you write inverse tangent, you're going straight to theta. If you write tangent, you're just relating the quantities. Okay? All you want is an equation that relates the quantities. So, because h is the opposite, we know the adjacent. What's adjacent? 3000. So it's, you know, it's pretty easy to just say, okay, tangent of theta is h over 3000. Does anyone understand this? Okay. Now, again, if you really want to solve for theta, you can do it and write inverse tangent. But remember, we need to find the derivative of theta with respect to t. But then you need to know the derivative of inverse tangent. If you don't remember that too well, it's probably easier to remember the derivative of tangent. So we can take the derivative here and use implicit differentiation. Okay? And I would suggest to do that. All right. So let's do it. So at this point, we take derivative, right? So now this is step number 4. We find derivative with respect of t. So on the left-hand side, what's the derivative with respect of t? What's the derivative of tangent? Secant squared of theta. But remember, chain rule, right? Times d theta dt. Everybody okay with this? Chain rule equals, and then you know, the 1 over 3000, that's a constant. So the right hand side is going to be dh dt over 3000. Questions? Do you understand this? Okay, so now d theta dt, I'm going to solve for it because that's what I want. So let me have a little formula for it. It's going to be equal to, okay, so I'm going to divide by secant squared, but then that's going to be in the denominator. What's 1 over secant? Cosine. So I'm going to multiply by cosine. Okay? Because divided by secant squared is the same thing as multiplying by cosine. Does everybody understand this? Remember, secant is 1 over cosine. So this is dh dt times cosine squared over 3000. Now we're going to put our data. Now we encounter a little situation here because we know, first of all, there's no h in the problem, right? So we don't have an h in here. But we know dh dt when h is 4000. So we have a number for this guy. We need to figure out a number for this cosine. Okay? Now, when h is 4000, now you have a fixed picture, right? With a 4000 here. And with that triangle, you can figure out the cosine. Now, you will have to find this distance, right? You will need the hypotenuse for that. Everybody okay with this? You should use your Pythagorean theorem to find this, and then find the cosine. The alternative would have been to use inverse tangent, and then if you use inverse tangent, you take the derivative of inverse tangent, that would only have h and dh dt. Okay? Because the information of the cosine or the secant would already be implicit in there. Okay? It's up to you how you want to do it. I kind of prefer this, but that's my personal preference. Anyways, I'm gonna go ahead now and plug in my data. I already know the HDT, that's 880, so we have a number for this, but I want to figure out a number for cosine, so let's do it. So let me say, when h equals 4000, we now have this picture. Here is theta, here is 4000, and here is 3000. Yes, that's the actual picture that we have at this moment in time. So I want to figure out the hypotenuse. Who can tell me what's the hypotenuse? That would be the square root of 4000 squared plus 3000 squared. Yes? So what is that? 4000 squared plus 3000 squared, and then square root, that's 5000. Okay? So the hypotenuse is 5000, so we can easily figure out cosine. So at this moment, when h is 4000, what's cosine? What is cosine? Adjacent over hypotenuse. So zeros are gone. So cosine is 3 over 5. Okay? So I'm gonna go put it in there. So when h is 4000, we get the d theta dt evaluated at this, at this point in time is gonna be dHdt at that moment, which is 180 times cosine, we figured out, is 3/5. So that's cosine squared over 3,000. All right, so solve this. Let's see, I'm gonna get rid of 1 0. So that's gonna be 88 times 9 over 300 times 25. I can simplify more stuff here. Okay, so I can divide this by 3 and get 100. And here I have a 3. Then I can divide this by 4. And what do we get? 22. And then I divide this by 4. I get a 25. So this would be 66 over 25 times 25. That's 625, right? 25 squared, 625. And this cannot be simplified more. So this is the exact answer, okay? And what are the units here? That is radians per second. Okay, so these are the units. This is the exact answer, but if you want to get an idea of what this is. So this is about, okay, let me circle this. But this is about 0.1056 radians per second. Okay, questions?
Can you do it using inverse tangent?
With inverse tangent. So using inverse tangent, so we are here. Tangent of theta was h over 3,000. So that means that theta is the inverse tangent of h over 3,000, right? So then we find d theta dt. What's the derivative of inverse tangent? Remember, this is 1 over 1 plus the argument squared. So that's h over 3,000 squared times the derivative of the inside. What's the derivative of the inside? dH dt over 3,000, right? And the good thing about this is that you don't have to worry about the cosine. You just plug it in, okay? So now, let's see. Let me clean this up a little bit more. So it's gonna be dH dt on top, and then here in the bottom we're gonna have 3,000 times 1 plus a squared over 3,000 squared, and I will distribute the 3,000 just to cancel this square right. So over 3,000 plus a squared over 3,000. Okay, so then let's plug in h equals, what was it? 4,000. So h equals 4,000. Then we get that d theta dt at this point equals dH dt, that's 880 over 3,000 plus 4,000 squared over 3,000. So let's see, 4,000 squared divided by 3,000. Okay, I don't like those. I'm gonna multiply top and bottom by 3,000. It's just that I want to find the exact answer. So then here I'm gonna have 3,000 squared plus 4,000 squared. Yes. Okay. So let's do this. So notice that it's somewhat implicitly we already have these calculations going on here. So 3,000 squared plus 4,000 squared. So that's gonna be 880 25, 1, 2, 3, 1, 2, 3. So these three guys are going with these three guys. This 0 is going with this 0. Let me make sure that I'm not missing something here. Square down, right? Yes. Okay, so that's fine. Let's see. So that's 88 times 3 over 2500. Then I can divide this by 4 to get a 22. And then 2500 divided by 4, that's 625. So we get 66 over 625. And that was radius per second. I mean, I don't know. I prefer to take derivative of tangent than have to deal with derivative of inverse tangent. But that's a personal choice. Okay? Of course, there is a price that you need to pay. If you do that, then there is this secant or cosine that pops up, right? That you have to figure out. But you just go to the triangle and you find it there.
I find it easier to do on inverse tangent.
Yeah, that's fine. It's a personal choice. But as long as you get the same thing, then no problem. Good. All right. Questions? Any questions on this problem? Are you understanding what we are doing? Okay. Now we're gonna do, I would say, the one that's that's more challenging than the previous ones. Okay, because here it has been kind of straightforward. You know, the step that I was saying that it was a challenging one was this one, right? Number 3, related quantities. But in the samples that we have done, it has been very straightforward to relate the quantities, right? There hasn't been anything strange happening. And let's do one in which it's not that straightforward to relate the quantities. You need to look a little bit deeper into the problem, okay? Like it's not right there in the surface for you to see. You have to think a little bit. So that's this one. Let's read. So a conical tank with vertex down, so you know the vertex of the cone is pointing down. It's 10 feet across the top and 12 feet deep. So those are the dimensions of the tank. Okay. Water is flowing into the tank at a rate of 10 cubic feet per minute. Find the rate of change of the depth of the water when the water is 8 feet deep. In other words, when the water is 8 feet deep, how fast is the water level rising at that point? Okay, that's what we want to do. All right. So, okay, let's see. So let's draw a little picture to kind of understand better what's happening. So we have a conical tank. So I'm just gonna draw here cone. Something like this. We have our tank, and then water is coming into the tank. Let's say, you know, there is a little entrance here, and then water is coming into the tank. Have fun with this. This is water. You know, there's water in the tank, and then the tank is being filled with water and so on. So water is coming into the tank. And we're being told at what rate this is happening. So this is happening at a rate of 10 cubic feet per minute. So water, and the rate is 10 cubic feet per minute. Okay, so we're being told that the cone is 10 feet across. What does that mean?
The diameter is 10 feet.
That's the diameter of the circle, right? So what's the radius?
About 5.
That means that this right here is 5 feet. Yes? And how high is the cone?
12 feet.
And this is 12 feet. Okay? This is what we're being told. And then find the rate of change of the depth of the water when the water is 8 feet deep. Okay? All right, so let's see. What are the quantities here? So let's see, and let's improve the picture a little bit more. I claim that we need to focus on two pictures here. One picture inside the other. It's true, everything is happening inside this tank. The tank is never changing, right? The tank is the tank. It's always 12 feet deep, and then it's 10 feet across. That never changes. The water is coming at a constant rate. But then there's something that's changing here. What's changing here with respect of time? The volume of what?
The water.
The water, right? So if you can think of the water as another little cone that is inside the tank, right? The cone formed by the water. Does everyone understand this? And then as time passes, that's growing, that's growing, that's growing. That's what we want to focus our attention on. Does that make sense? In other words, inside this, there is another picture that we need to pay our attention to, okay? Which is, we have this right here, and this is the cone formed by the water. Yes? This is the guy that we are going to have our quantities on, because, our tank, it has a constant, it has the same radius, the same height, that doesn't change. What's changing is, the quantity that changes here is this cone formed by water. Do you understand this? So now, what are the relevant quantities here? The radius of this, right? We're interested in knowing that. What else is another relevant quantity? And okay, volume. Yes, volume. What else? The height. After all, that's what we are after. We are after the depth of the water, right? So we are after the height. This guy. So in other words, let me go back to the picture. So R and H. Okay, R, H. So now let's write this down. So what are the quantities? In this problem? So what are the quantities? First of all, and does everybody understand that these three quantities, they all depend on time? As time passes, there is more water coming in, and this is growing, right? So we have R, which is R of T, and this stands for the radius of the cone formed. Is important, not the tank, but the one formed by water. Okay, and it appears that we're using feet here. Next, we have H, which is also a function of time. This is the height of the water. At time t, once again, it's going to be measured in feet. And then B is the volume of the water, or volume of the cone, right? So this is also a function of t. The volume of water at time t. And this is given in cubic feet. Everybody okay? And then finally we have, this unspoken variable, which is t, time, because everything is depending on time, right? And we have t, which represents time, and we're measuring time in this problem in minutes. It is clear? Okay. What's step number 2? So let's get the data. So let's make sure that we see what we're given and what we need. So what are we given?
We're given
The rate of the volume.
So we're given dV/dt, right? What is it? 10 cubic feet per minute. So it's constant. This is always happening. Yes? So it doesn't change regardless of time. So dV/dt is always 10. Okay, it's good. dVdt is equal to 10. What else do we know?
No H.
What do we know about H?
That's 8.
Okay, but you are now part of the question. We don't know H. So we know that we want to find the height of the water when H is 8. Remember, H is changing, right? So that 8 right there is just to tell you to fix the moment in time. Yes? So they don't give us more information now. The question comes, find the rate of change of the depth of the water. In other words, what is that in mathematical symbols? Rate of change of depth of the water. Without symbols, what would that be? Of what? Of H with respect to what? So dH dt. Yes? So we need to find dH dt when H is 8. Do you understand this? That's all the given information. So we need to find dH dt when H is 8. Questions? All right. That's it. We're not giving anything more. Now, what's the next step? So relate quantities. How do we do this? The volume of the cone. So, anybody remember the volume of a cone? Is 1/3 area of the base times the height. So in this case, what's the base?
It's
2R.
What's the base? What's the shape of the base?
Circle.
It's a circle. So what's the area of a circle?
PR squared.
Pi r squared. So it's 1/3 pi r squared times the height. Okay? I'm giving you this pattern of area of the base because, for example, if the problem is about a pyramid, it's the same thing. The formula for a pyramid is 1/3 area of the base times the height. But if the base now is a square, then you need to plug in the area of the square instead of a circle. Okay? By the way, you will be able to figure out all of these formulas. You will learn where these formulas come from in Calculus 2. When you, as an application of integration, you're gonna use it to calculate volumes of solids. Okay? And in there, you will see where these formulas are coming from. All right, so once your classmate is actually doing an honors project, and the project is about this, to be able to understand where these formulas come from and how to obtain it using integration. Okay, anyways, here we're going to use a formula for volume. So the volume of a pyramid is 1/3 area of the base times the height. Well, in this case of a cone, and the area of the base is a circle, so that's pi r squared times h. Okay, so here we relate the quantities. So the volume is 1/3 pi r squared times h. Do you notice a problem? What problem do you notice?
We don't have R.
Exactly. Notice that if you look at the given data, you know, when you take derivative, the r is not going to disappear. Does everybody understand this? In fact, if you take derivative right now, both r and h are what? They're functions of t. So when you take derivative, you will need to use product rule, right? And r is not going to go away. And there will also be an dr dt popping up. Yes? We don't know r, we don't know dr dt. We're not given that information. So we need to do something about it. Do you understand this? So before, the problems that we have had so far, after we related the quantities, then it was straightforward because all the information that we needed was already given to us. It was just a matter of going back, plugging, and so on. Now you should realize that at this point, yes, here we're relating the quantities, but we need to do something else because there is this r here that we don't know anything about. Right? Remember, this is the r of the water. Okay? We're not giving anything about R, we're not giving anything about dRdt, which is gonna pop up when you take the derivative. Is it clear what the situation is? So, what do? We go back to square one. Let's stir our situation a little bit more and see what we can do, okay? So remember, we're giving information about V, and we're giving information about H, right? Our job is to use that information to hopefully say something about R. Now, per se, V has no business here in the picture, right? This picture is really just R and H. Now, by the way, notice that we haven't used, what we have not used yet. As it stands, there's something that we haven't used. What is it that we haven't used? We haven't used information on the tank, right? And you should understand this has to play, and this has to play an important role. If the tank is super big, it's going to take longer for the water level to rise, right? So the dimensions of the tank, they have to play a role here. And we haven't used the 12, and we haven't used the 5 or the 10, however you want to call it, right? So this is the moment in which this better comes into the picture, because otherwise, when is the moment? Because there is no other place for it to show up. Okay? So so now the question is, how do you relate H and R, or how do you relate R with H, knowing that you have this extra information? So I'm going to give you a minute, and then I will start giving you little hints. So hopefully you can see. Remember, we want to say something about R. Okay? See, let me actually make it more straightforward, more concrete. We want, at some point, we're going to plug in H equal 8, right? When H is 8, can you tell me what is R? There you go. That's your question. Find R when H is 8.
Can we express R in terms of volume and height? Like so for R using the volume parameter?
So, but do you know the volume? You don't know the volume. You know the VDT, but you don't know V. If you knew V, then yes, you could do that. But you don't know V.
Would you use the ratio of 12 to H somehow?
Okay, that's a good idea. Where is that ratio coming from?
8 divided by 12, or 12 divided by 8. And use that to find 5 over R or something.
Okay, good. So let me spell out what your classmate is saying. There is a secret geometric relationship going on here. There are actually similar triangles popping up. So I'm going to stand this here. Okay? Let me stand this here, and I'm going to take a snapshot of this cross section of the cone. You mind that I cut this in the middle, and then half again. I'm going to write, there are two right triangles involved here, one inside the other. Okay? So let me write it down. Good. So we have this picture. Where this is 5, this is 12, okay? And then over here, we have R, and we have H. And this little triangle here corresponds to the water. Does everybody see that from the cone? Do you see it? Okay. Now, here we have, there are two triangles. There is the big one and there is the small one, and they're similar triangles, okay? Because they both have 90-degree angle, and for example, they share this angle in common. So therefore, this angle over here is the same as this one over here. So they have the same angle, so the triangles are similar. When triangles are similar, some proportion, the size, corresponding size are proportional. Remember this? So this angle is common, and then this one corresponds to this one. Okay, so these are similar triangles. So similar triangles. So there is a proportion that we can write. So corresponding sides are proportional. Now, let's see. The easier way to write the proportions is just pick one of the triangles, write the sides on top, and then in the bottom you're gonna write the corresponding sides of the other triangle, and then you solve for what you need. Okay? For example, what's your favorite triangle? The small or the big one? The big one. Okay. So tell me the size of the big one.
12
So 12
or 8.
and 5, right? 12, 5. Now, if you want, you can put here another one, which it will be the hypotenuse, but that hypotenuse will correspond to this hypotenuse, and we don't really care about that. Okay? So I'm not gonna bother myself with that. So you know that there are some proportions that we can write. So here I put the size of the big. Now let's put here the corresponding size of the small. So how do you determine corresponding size? I'm doing it like this to remind you if you don't remember this. So on the big one, this is 12. You have to look at the angle. So what's the angle corresponding to this side? It's the opposite one, which is this one. So go to a small triangle. What's the angle which is the same as this one? This one down here. Yes. So what's opposite to this? Is h right here. Okay. So 12 corresponds to h. Those are corresponding sides. So 12 over h equals, so 5 is opposite to this middle angle right here. So r is the corresponding side. You understand this? So 12 over h is the same thing as 5 over r. So for example, if I tell you now that h is 8, you can easily figure out r by solving this proportion, right? Multiplying. But let us not do that. Let's go ahead actually and write r in terms of h. That's really what we want. We want to get rid of r in our relationship downstairs. The one that we have down there, we want to get rid of r. We have it right here. Notice that this is always the case, regardless of h. We always have this behavior because this little cone is inside the big one. Do you understand this? So what's r equal to from here?
5 each over 12.
So that's going to be 5 times h over 12. Do you understand how to solve proportions? Just cross multiply and then you solve for what you need. Okay? So this means that 12 times r equals 5 times h. Then divide by 12. So, for example, if you want to know what is r when h is 8, you put it here and then you compute. But I'm going to take advantage of this big expression and put it back here. Okay? Let's put it here because I want to get rid of the r in my main formula. Do you understand what I'm about to do? I'm going to get rid of the r. So we know that r is 5h over 12, so let's plug in. So that's 5h over 12 squared times h. And then rewriting this, what we have. So let's see, 5 squared is 25. So we're going to have 25 pi over, that's 144 times 3, 432. Let me actually leave it as 3 times 144. H cubed. So again, 5 squared, that's 25, it's a pi, the 3, I left it there. 12 squared, that's 144. Put it there, multiplying. And then we have h squared times another h. That's why we have an h cubed. The reason why they multiply is because now when you take derivatives, this 3 comes down and we cancel this one. Okay? So I don't have to worry about dividing. Okay, so now we have a relationship between the quantities, but now we eliminated the one that we didn't have information on, right? We're not given anything about r, that's fine. Now here we have a relationship between b and h only. And this works for us. Now we are ready to take derivative. So now comes step 4, which is find derivative with respect to time and solve. So dv dt is going to be equal to 20. So all of this is a constant, so it stays here. And then this is going to be 3h squared times dh dt. 3's are gone. So we get dVdt is 25 pi over 144 times a squared times dH dt. And so that it doesn't look too messy, I will just plug in right here. So now let's plug in what we have. We know dVdt, that's equal to 10. We know h, that's equal to 8. And we know dH dt, no, we don't. That's what we're going to find. So when h is 8, we get 10, because dVdt is always 10. It's 25 pi times a squared over 144 times dH dt when h is 8. So we can solve now. So dH dt equals, let's see, I'm going to multiply and divide by that quantity, and then I will simplify. So that will be 10 times 144 divided by 25 pi times 8 times 8. Put it 8 times 8 so that it's easier for me to simplify. All right, so let's start with the simplifying. Let's see. Half of 8 is 4, half of 10 is 5. This 5 is gone with the 25, give me a 5. Now, we do 144 divided by 4? Yes. Half divided by 4, and then here we get a 36. And then divide this by 4, you get a 2. Divide this by 4, you get a 9. So we end up with 9 on top. And then in the bottom we have 10 pi. Just do this however you want. Just simplify however you want. Just make sure that once you are here, you isolate and then you simplify this successfully. How you do it is up to you. Okay? So we get 9 over 10 pi, and what? So this dH dt, so that would be feet per minute. And it's always helpful to have an idea of what this is. 10 times pi, flip it, times. So this is about 0.29 feet per minute. Okay, that's how fast the water level is rising. Okay, any questions on this example? So this one is slightly more, more complicated than the previous ones because there was this hidden quantity, this quantity that we're not giving any information. So you need to go back and look at the problem a little bit different. Okay? So be mindful of that in case that this happens in the homework. In the homework, you see stuff with pyramids and things like that. Remember that you have always the similarity property working behind the scenes. Yes.
What buildings you're option?
3.